Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon to all of the audience that are watching this distinguished lecture series. For your information, this is lecture number 9 from its series that is proudly brought to you live from the Faculty of Engineering, University Technology Malaysia. This distinguished lecture series is an initiative from our faculty at UTM to initiate and improve our networking with international scholars around the world by taking the opportunity from the current COVID-19 pandemic. As most of us are restricted in terms of the movement and socializing. My name is Amirul Abu Bakar, a senior lecturer from the School of Civil Engineering UTM, and with us this afternoon is Professor Roger Alexander Falconer, an Emeritus Professor of Water Engineering from Cardiff University, UK. It is good to acknowledge that Roger is one of the key persons that has supervised me during my PhD research at Cardiff University, and it is honored to have him with us this afternoon. This afternoon, Roger will be talking about global water security, a very crucial topic that needs to be further discussed, and with an important resolution to this issue, the integrated water resources management. Without wasting time, I will pass the screen to our Dean of Engineering, Professor Datuk Insinyur Dr. Muhammad Rafiq bin Datuk Abdul Qadir, for warm welcoming words prior to the beginning of this lecture. Over to you, Datuk.
Thank you, Amirul. Assalamualaikum warahmatullahi wabarakatuh. Hello, welcome everyone, and welcome to UTM Engineering Distinguished Lecture Series, our 9th lecture in this series. My name is Rafiq, and I am the Dean of Engineering, University Technology Malaysia. Today, it is my utmost pleasure to welcome Prof. Roger Falconer to our program. A bit about our presenter today. Roger is Emeritus Professor of Water Engineering, Professor of Water Management in 1997 until 2018, and Founding Director 1997 to 2015 of the Hydro Environmental Research Centre, School of Engineering, Cardiff University. He was previously Professor of Water Engineering and Head of the Department of Civil Engineering, University of Bradford, 1986 to 1997, and Lecturer in Hydraulic Engineering, University of Birmingham, 1977-1986. He has been involved in a wide range of research contracts on hydro-environmental modelling, and his models have been used in over 100 environmental impact assessment studies worldwide, and provide the engine for the commercial 2D model Flood Modeler Pro. He has published over 400 papers in journals and conference proceedings, and has given over 530 presentations to a range of learned societies and universities worldwide on hydro-environmental modelling, including water security, water quality, flooding, and tidal energy. Roger is a Fellow of the Royal Academy of Engineering, Foreign Member of the Chinese Academy of Engineering, and Fellow of the Learned Society of Wales. He is also an Honorary Member of the International Association for Hydro Environment Engineering and Research, IAHR, and Past President of IAHR 2011 to 2015. He has received many awards for his work, including the Royal Academy of Engineering Silver Medal in 1997 and the IAHR Ippen Award in 1991. He chaired the Civil Engineering Sub-Panel in the 2014 Research Excellence Framework and consults regularly on projects worldwide on flooding and environmental assessment impact studies. So that is a brief biography of our speaker. Here now is Professor Roger A. Falconer from Cardiff University, United Kingdom, to talk about global water security, integrated water resources management. Prof. Falconer, over to you.
Good afternoon, ladies and gentlemen, and thank you, Dato Rafiq, for that interesting introduction. I'm going to talk to you today about global water security, and I'm first of all going to address the issues on a global scale and some of the challenges we face, and then I'm going to take from that the important issues of integrated water resources management at the local level. And firstly, I would like to point out that global water security has achieved growing concern worldwide over the last 10-15 years in particular, And a number of studies have been undertaken, and some are shown here. One I was personally involved with, the Global Water Security, undertaken by the Royal Academy of Engineering in the UK. So let me first put things into perspective. On the one hand, it would appear that we have plenty of water, and why are we worried? But on the other hand, this water is a limited resource. The total global volume is 1.4 billion cubic kilometers, which is a large amount. However, there are only 35 million cubic kilometers of fresh water. And of that fresh water, much of it is locked up in ice. So we're left with only 105,000 cubic kilometers accessible, or 0.01% of the total volume. And if you look at the drawing on the left here, you can see that dot. Now, some of the challenges we face include, for example, climate change. You would be all familiar with the challenges of climate change. In the UK, we are planning for an expected global temperature change in the ideally below 2 degrees. And we're expecting sea level rise to increase by typically 1.3 plus meters by the end of this century. Another challenge which we face globally is the population growth and the impacts of population growth. In 2009, the population on the planet was about 6 billion. And Sir John Beddington, who was then our chief scientific advisor in the UK, gave a global lecture entitled The 2030 Perfect Storm. And it was predicted that by 2030, we would have a global population of 8 billion. We're already well over 7 billion. That increase between 2009 and 2030 means we will need to provide 50% more food, 50% more energy, and 30% more water. So again, this is an added challenge on top of climate change. And then we look at some of the issues of global water security. If we just look at the water in rivers, for example, the ancient Romans had better water quality than half the people alive now. I live out in the Yorkshire Dales in the north of England, very pristine area, and even the local river here has very high levels of fecal coliform under flood conditions, and that's in the UK. But the next slide below shows that 70% of the world's freshwater supply is devoted to agriculture. And this is where we really need to focus our efforts in the future if we are to have plenty of water for all. So let me summarize briefly some of the key challenges. There are 1.25 billion people have no access to safe drinking water on the earth today. 2 million, mainly children, will die of diarrhea. Now, it's extremely unlikely that any child will die of diarrhea in the UK. And it would probably be on the main news if that were to happen. So we in the UK are not really familiar with the impact of water security when we see 2 million children dying most years of diarrhea. 2.4 billion people do not have access to basic water sanitation. 1.4 million contract annually hepatitis A. Women in developing countries walk typically 6 kilometers daily to get water for the family. When you think of all the sophisticated technology we have on the planet today, I find it unbelievable that women still have to walk to get typically 6 kilometers a day to get water for the family. And flooding can cause many deaths globally. The Aceh earthquake in Indonesia and the subsequent tsunami, traveling at a speed of typically 800 kilometers an hour, the same speed as a 747 jet. That would have taken 3 hours to get to Sri Lanka. And you would have thought that with all the sophisticated technology that we have worldwide today, we could have got a message to everyone in Sri Lanka. We had 3 hours to send the message to get up to high ground. But we failed to do it, and typically 240,000 people lost their lives. And most people today, doesn't matter what their standard of living, have a mobile phone. And more than half the hospital beds in the world today are occupied by people with water-related diseases. So it is a challenge, and it is a global challenge. And every country has to play its part in trying to address this global challenge. So we have the UN Sustainable Development Goals, aiming to achieve a number of these goals, if not in their entirety, ideally, by 2030. The COVID-19 current pandemic, of course, will have disrupted things a bit, but nevertheless, those are the goals. And these are some of the aims of those goals. If we look at SDG 6, for example, this requires access to safe and affordable drinking water, access to adequate sanitation, improvements in water quality, increased water use efficiency, integrated water resources management. I'm not sure people always know what that means. Protect and restore water-related ecosystems. That's a big challenge. Expand international cooperation. Not easy. And strengthen the local community participation in water and sanitation management. So there's a lot of big challenges there. And we now only have 10 years left to achieve those goals. So let's look at the water, food, energy nexus. In that slide by Sir John Beddington, I told you that we would need roughly between now and 2030, a 50% increase in water, food, and energy. And these are interlinked. So we need water to produce food. Food can give us energy as humans. And energy and water provides energy through dams, for example, and so on. So there is this water, energy, food nexus. And if one is disrupted, it affects the others. If there's no water in the dams, then there's no energy for the hydropower scheme, and so on. If we don't have enough food, then you and I don't have enough energy, and etc. And I would question whether we can just consider the carbon footprint in isolation. The world is currently focused on the carbon footprint, but maybe we should be applying an equal amount of emphasis on the water footprint. So, summarizing some of the key pressures, climate change is leading to significant challenges: sea level rise, increased storms, increased temperature, global temperature. The population is likely to increase by a further 40% to 11 billion by the turn of this century. I won't be around then, but there'll be plenty of you that will be. The population is moving increasingly from the rural areas to the cities where the jobs are, and particularly coastal cities. So we're seeing a significant redistribution of the population globally. Food production is going to need to increase by 40% over the next 50 years. Industrial demand, you can just see in China, for example, the big increase in the need for cars. That we're going to need new energy sources, particularly as cars move to electric energy. So people are also going to become wealthier, as we've seen in many countries across the world. That means they have more disposable income. More goods are purchased. If I just compare my own situation when I was a child to today, the number of goods and commodities in the home has increased dramatically. As people become wealthier, they spend more time eating out, looking at a bigger variety of diets. They change their diets, and in many countries, they're increasing their meat consumption. So if I just take this point, if we're changing diets, that often demands more water for the same number or per person. 1 kilogram of beef, for example, requires 15,500 liters of water. 1 kilogram of wheat only requires 1,300 liters of water. So let's look at the water management and the water cycle. On the left-hand side here, you see the water falling from the cloud. You have 100% of the water drops from the cloud. It then either follows the blue path, which is your river, and only 36% of the water that drops from the cloud typically ends up going back to the ocean. Some of the water will go straight into the ground. That's the green path. Let me follow the blue path in particular. So you have water going down your river, and then we take water off at an abstraction point, probably just upstream of a major city near the coast. And that water is taken into a factory to produce, let's say, paper. Now that paper can be distributed internally within the country. So that water from that river is used for domestic consumption. Or the paper could be distributed and sold overseas, which means that the water used in a country, let's say Malaysia, to produce paper is then exported to the UK, for example. So that is an export of effectually virtual water from your country to my country. And my country happens to be one of the worst in the world when it comes to virtual water. Similarly, if we go down the path below, you can see food. So if we take coffee, for example, we know we do not grow coffee in the UK. So any coffee that's imported into the UK comes from places like Brazil or Kenya. And that comes down through the virtual water path. The water used to produce that coffee is used in Brazil, but the coffee is drunk in this country. The problem is in this country, like most countries in the Western world, people tend to think that the only amount of water that's needed is the actual water that's in the cup of coffee. So when we look at the water footprint of a nation, the water footprint, the total water footprint of, let's say, the UK or Malaysia, is the water consumed within that country and used to produce goods and services. So beef, for example, for the meal within the nation. But there are two components of this water footprint. There's the internal water footprint. So the cattle are reared on the fields, for example, and then that's converted to beef, and that beef is used in, let's say, Malaysia. So that's your internal water footprint. You've used your own water to grow the crops, to feed the cattle, and so forth. However, if you sell those cattle overseas, like we get lamb here, for example, from New Zealand, then that's an external water footprint. No, sorry. The external water footprint here is something you buy in from another country. So the water footprint of a nation is the water used internally, plus the virtual water imported, so the coffee from Brazil in the case of the UK, minus any commodities we produce in the UK, for example, and sell overseas. So if we look at the UK, our internal water footprint is typically 38.6 gigacubic meters per year, but our external water footprint is almost twice as big. And that's mainly from agriculture. And you remember I told you in the beginning, 70% of the fresh water is used for agriculture. So now let's look at this virtual water footprint. If we think of 1 cup of coffee, the total amount of water used to produce 1 cup of coffee is typically 140 litres. These come from the water footprint network of the University of Twente. Now, if we buy this coffee in the UK from Brazil, for example, then most of these 140 litres will be water in Brazil. If we eat a steak, we would be talking in terms of 26 bars of water in total for that steak. But I want to focus, if I can, on cotton, because we produce no cotton in the UK. And if we look at a pair of jeans, for example, then this would equate to typically 10,850 litres of water needed to produce a pair of jeans. And that would require 73 bars of water. And most people in the UK wear cotton clothes. My trousers on at the moment are probably cotton. My shirt is cotton. And where does that come from? Well, that comes in the main from countries like India, Pakistan, Kazakhstan, and the East European states. So the amount of cotton, and when you and there are issues we can look at to address these changes, because a man can wear the same shirt, same white shirt, same grey suit every day of the week and read the news, and nobody comments on it either way. His water footprint is relatively low. But in the Western world in particular, but not only the Western world, the woman would be expected to, if she were reading the news, for example, probably have a different dress on most days of the week. She certainly wouldn't be wearing the same dress 5 days a week, unlike the man who can wear a grey suit and a white shirt. And that has a huge impact on water security and the external water footprint from countries like India and Pakistan, for example. And if we look at Kazakhstan, the impact of virtual water in terms of cotton has meant that this lake has completely disappeared. So what are the solutions for addressing global water security? Well, one is desalination. We see lots of desalination plants being built in the Persian or Arabian Gulf, for example. It's expensive. It has a low carbon footprint. And potentially, if the tidal range is small, then the long-term hydroecological impacts can be significant. We can look at conservation and water reuse, but this is really dealing with things at the 4th, 5th decimal place. This is domestic consumption. In the UK, the typical consumption of a human is 150 litres a day. If you don't run the tap while you clean an integrated water resources management, and historically, we have not looked at this in an integrated manner in terms of holistic modelling. And we need to be doing much more of this later, and I'll show you an example in a minute. We need improved water quality in catchments and river basins. So if we're going to buy cotton in the West, for example, from a country like India, we need to be prepared to pay more so that the water is treated by the Indian farmers before it's put back into the river, highly polluted, only for young children further downstream to be swimming and drinking that water. And one approach here is to look at coastal reservoirs, which offer an increasing opportunity to deal with water security of coastal megacities. We see this in China in particular, in Shanghai. And I know that from my own links with Malaysia, there is a lot of interest in coastal reservoirs now in Malaysia. So let's look at the cloud-to-coast integrated water resources management concept. We have the catchment model, groundwater models, sewer models, 1D river models, 2D estuary models, 3D ocean models. All these tend to be focused in consulting companies, for example, where the different expertise for each of these modeling groups. We need to model hydrodynamics, water quality, and sediment transport. And very often these people don't really speak that well with one another. So we get a disintegrated solution. When the particle drops from the cloud, the package of water, it lands on the field. There is some waste in the field, let's say a cow pat, waste from a cow, for example. The E. coli is then picked up in the storm, taken into the catchment, sewer, groundwater, or river, and so on. Now, that particle of waste doesn't know whether it's in the catchment or in the estuary. So we need to make sure that these models are fully integrated. And then, of course, we can go on to design an effective scheme. Our traditional designs have not always been the best. We take water in upstream in our river. We then distribute the water around the city. We then send it to a sewage treatment works, and then we discharge it to a long sea outfall. So this part of the river, from the intake here right down to the coast, is often depleted, giving us low flows, ecological impacts downstream of the extraction site. If we're going to solve this problem, we need to look again at an integrated approach, take the water in at one site, distribute it around the city, and then send it back and put it back into the river, just slightly downstream of the abstraction point. And then farming. 70% of our food comes from, 70% of our water is used in food production. I know in the US at the moment, for example, they're doing a lot on vertical farming and trying to use far less water and manage the crops. And you can see here in this picture, the food produced here is only requiring 1% of the water that would be needed for food growth vis-a-vis traditional farming where the crops are grown on land. So I'd now like to, quite clearly we have to think globally in terms of water management and in the water security sense. And we have to educate more people in countries like my own, for example, to appreciate that when you buy a cotton item of clothing, you are having a significant impact on the water resources in a country like India or many parts of Africa, for example. So that can be quite clear, but we also need to look at this at the local level. And I want to take an example here of integrated water resources management for a key river in the UK called the Ribble, and the impact that anything coming from this river might have on our Faecal coast. Now, this is the River Ribble, and it flows into this coast here called the Faecal coast. This is the northwest of England. And Blackpool is one of our premier seaside resorts. So this is Blackpool in 2018 in the picture, the color picture. And even today you can see this is still a very popular seaside resort in the UK, probably one of the most popular. And back in 1965, you can see it was extremely packed and extremely popular. But this bathing beach has had problems. It failed to meet in the mid-1990s, it failed to meet the EU 1976 Bathing Water Directive. Storm sewers and sewage works discharging along the coast were thought to be the problem. Combined stormwater and sewer overflows discharged it into the watercourses and rivers, and field surveys were undertaken to establish the inputs and failure levels of the compliance. However, the surveys didn't solve the problem. It didn't really tell us what was the problem, and modelling was needed. The water company invested $800 million from about 1993 to 1996, building 3 new wastewater treatment works, 5 new larger pumping stations, but still there were challenges of non-compliance with the EU Bathing Water Directive during the summer bathing season. So my colleagues and I at the Hydro-Environmental Research Centre in Cardiff undertook studies from 1998 to 2002, developing a hydroepidemiological modelling tool going from the tidal limit right along the coast. We wanted to quantify the impacts of the sewage overflows in the Ribble estuary and on the bathing water quality along the coast. We wanted to investigate the impact of different tides, winds, river flows, allow for continuous and intermittent discharges, and include urban and rural changes due to CSO inputs as boundary conditions, and then propose management strategies for the river basin. So we first of all calibrated the model. This just shows the results at one site. We predicted the water levels very accurately, and the currents were also predicted very accurately. Now, if you're a researcher in the UK, this is not ideal, because if you get good agreement between your model and your data, it's very difficult to justify more research funding for your computation model. And then we tried to model fecal coliforms, and we again found, on the whole, we got pretty good predictions. And any of you that have been involved in measuring fecal coliforms will know that you can measure fecal coliforms at 2 sites in a river a few meters apart, and they can vary by 2 or 3 orders of magnitude. But we noticed one big difference here. In the dry river flow, the fecal coliform levels are down at about 1,000 and less. And when we have wet river flows, they're up at 40,000 plus. So much higher fecal coliform levels during wet weather conditions. In other words, it had been raining. And when we looked at this compliance point, which is this black dot here, I hope you can see it. The left-hand animation here shows river flows for dry weather conditions. And you can see that the fecal coliform levels, the light blue and the green, are down at 100 to 1,000. And there's no failure at the compliance point, the black dot. When we turn to the picture on the right-hand side, we can see that the fecal coliform levels passing that non-compliance point are over 1,000 and nearly up, and in some cases up to 5,000. So We can conclude from this model simulation that the cause of the problem is actually the coliforms coming down the river, which then end up moving up here to the Blackpool coast and this Faecal coast. So in 2010 to 12, funding was provided for us to do more comprehensive studies, integrating our 1D and 2D models and linking them in a much better manner. We found that we had different values for the kinetic decay rates, different values in the 1D and the 2D models between the dispersion and diffusion coefficients, different flow areas at the linking point, different values of the formulations for the roughness. In the 1D model, we used the Nicorazzi KS function, and in the 2D model, we used the Manning's N. We had a simplified treatment of decay and source inputs from highly episodic points and diffuse source inputs. And we were now using 3D modeling of the hydroepidemiology in the coastal zone. So this is an example of the difference in the decay rates in the original model between the 1D and the 2D, both of which were calibrated for the 1D domain and the 2D domain. And you can see there are differences. For example, T90 value at night was 110 in the 1D and 81 in the 2D. We then looked at the dispersion diffusion coefficients. In the 1D model, we were having values over 100. And in the coastal model, the 2D model, we were having values down at typically 3 or 4 meters squared per second. So why should there be big differences in the dispersion between the river and the coastal zone? So when we fully integrated the model and made sure that we didn't just fine-tune the dispersion coefficient, for example, to calibrate the 1D model accurately or the 2D, but used the same formulation in both, we found that our model was much more sensitive to land use changes in terms of predicting the fecal coliform levels at the compliance point. And then in 2011 to 2016, we were funded to undertake a totally new study and a much more comprehensive study. Up until now, we had only gone up to the tidal limit. The EU Water Framework Directive became much stiffer in 2016 and was to be implemented from 2015 onwards. So whilst the Faecal coast was now complying with the 1976 Bathing Water Directive, it was not going to meet the criteria of the 2006 directive, which was going to come into play in 2015. There were concerns about the impact of recent land use changes on the river and coastal basin water quality. We needed to include catchment characteristics and impacts in the linked model. We needed to model both rural and urban catchment inputs. And we needed to improve the ability to predict the exposure to and the health impact of fecal indicator organisms in the coastal waters. So we undertook a new study which went right up into the catchments. So we modeled the catchments. We estimated the urban point and diffuse loads. I'll come back to that in a minute. We collected new data on the E. coli loads and fluxes. We collected lots of data. We calibrated and validated the integrated process models from the catchment all the way to the coast. We produced a qualitative health impact assessment to predict gastroenteritis impacts. An informatics tool has been developed to predict and protect the coast. And we produce recommendations for policy, make data formally, models, etc., available to stakeholders. So here is the model domain, including the outer sea, here, the estuary, and the catchment. We had a 3D Irish Sea model, our own model. We had a 2D, 3D integrated model in the estuarine environment. We used the Stanford HSPF catchment model, and we developed our own 1D, 2D river model. And we used the model InfoWorks for predicting the urban inputs. So we modeled 28 different catchments. all discharging into the estuary here, and then flowing up onto the Blackpool beaches. These catchments consisted of rural and urban. Some of these catchments here were highly urban. The city of Preston here, for example, and up here we have much more rural sheep and animal farming. We took measurements in the sea, measurements in the river. We used dye tracer studies, bottom left, and we took samples, including sediments, day and night. These are the sort of inputs we had from the catchment. The cow goes in the stream, for example, bottom left. It then passes its waste out into the river directly, and we have a very high concentration of E. coli from the cow in the river, for example. That can be solved quite easily by fencing off the river, but it's not that easy to implement that as a directive. Also, the animal leaves the waste on the land. The storm comes, picks that up and takes it into the brook, from the brook to the stream and so forth. And on the top right, the farmer spreads the waste over the land. And at the bottom, the farms are discharging their waste into septic tanks, and a lot of that goes back into the groundwater. So we use the American bacterial indicator tool to estimate the loads on the land. And here we can see one particular catchment, Catchment 2, which has both rural and urban inputs. And if we look at the HSPF predictions for E. coli from cattle, the purple is in the urban area, and you can see that's relatively low compared to the much higher levels from the green, which are basically the cattle. And you can see here that in certain catchments, there's a high rural input, whereas we have focused historically very much on the urban inputs and tried to reduce the CSO inputs. So we had a comprehensive 1D river network model, picking up the catchment inputs and taking those fluxes of sediments, and in particular E. coli and enterococci, from the upper levels of the catchments here, picking up urban inputs all the way down, and then down here into the coast and along into the sea. So first of all, we needed to check our model, the river model. Generally speaking, it gives water levels pretty accurately for a 1D model. The discharges are shown below, and again, they're quite encouraging. And then we look in the estuary. We're modeling suspended sediments, and we can see, particularly in the bottom picture here, it's generally pretty good. And a lot of assumptions in the theory of suspended sediments. And the E. coli predictions are pretty encouraging through this basin as well. So when we have set up here our integrated model going from the catchment to the coast, we can see we're getting pretty good predictions of conditions downstream. And then we can play tunes on the model to find out what is causing the problem and what can we do to reduce the high E. coli levels downstream. So this is our 3D model in the open sea and the boundary conditions of the coastal model. And here we can see from the measurements there are significant differences in the decay rate for E. coli, for example, between freshwater and saltwater. So the T90 value in dark conditions in freshwater is virtually non-existent. It virtually doesn't decay. So it doesn't decay as it travels through the river, freshwater, at nighttime. In contrast, when it's in the coastal water, it decays by 90% per 33.77 hours. So in other words, the E. coli decays very much more rapidly in saline water than freshwater. So we modeled the coastal conditions, and again, we got pretty encouraging results, as you can see from the plot here. And then we modeled in the estuary the suspended sediment concentrations, and in particular, the E. coli. And we come up with a very interesting conclusion. what we found was that actually a very important mechanism for transporting E. coli and enterococci from the catchments some distance upstream was in the sediments. The green line here shows the the blue line shows the fecal indicator organisms measured in the water column. The red line shows the fecal coliform levels adsorbed on the sediments, moving with the water under flood conditions. And then the fecal indicator organisms, E. coli in this case, is desorbed from the sediments in the water column. So the E. coli could have been stuck on the sediments. Oh, and sorry, the green line here shows you the very high concentrations relative to the water column on the bed. So when the sediment, when E. coli goes into the sediments, it can be held there and not decay for some considerable amount of time. Then the storm comes, picks up the sediments, and E. coli can go back into the water column, increasing the inputs further downstream. So the conclusion from this study is that if we're going to look at integrated water resources management and improve the water quality in rivers, we must also model the suspended sediments. So the conclusion of my talk: hydroepidemiological measurement and modeling is a subject of increasing global significance, and things are becoming more challenging. And this is clearly an area of considerable importance in every country, in my experience, across the world. Many water quality process models include crude representations of the biochemistry and kinetics. We as engineers have spent huge amounts of time modeling, measuring friction in channels and so forth, and we go to great pains to make sure that we get the roughness characteristics and dispersion diffusion characteristics modeled as accurately as possible. But then we tend to use water quality formulations and kinetics, which is relatively crude. And what this has proven to me is that we have to work as a team with biochemists, ecologists, and so forth. It's no longer good enough for an engineer to be trained in hydrodynamic modeling and add on water quality processes without bringing into the team very strong expertise in biochemistry, kinetics, and so forth. Integrated water resources management needs much more holistic solutions from the catchment all the way to the coast, whether it's to do with flooding, water quality, or drought. We have to model from the top of the catchment right down to the coast to get the best solution for all our citizens living in our country, whether yours or mine. E. coli concentrations in the Ribble and the Faecal coast were highly dependent on catchment inputs. So cattle on the land, for example, and cattle in the streams significantly affected the water quality. And finally, E. coli adsorbed on the sediments can be an important mechanism for transporting E. coli or any other water quality constituent through the river basin from the catchment again right down to the coast. So thank you very much for your interest, and I hope that I can answer any questions you might have. I can't hear you, Amaru.
Okay, Roger, thank you very much. Thank you very much for your lecture. Very beneficial lecture series regarding water security, global water security, and the idea of tackling this global water security through the integrated water resources management. Okay, we have several questions here. Okay, the first one is this is related to the COVID-19 issue, spread in the water, as we know earlier. So the question here is, since our government already allowed to open the swimming pool, so how do we address the issue of COVID-19 when people want to go to swim, especially as we read from the news that the Brazil has allowed their citizens to go outside, especially for bathing at the beach.
I don't think anybody really knows. Oh, sorry. Can you hear me okay?
Yeah.
Sorry, I just need... That's better. Can you hear me now?
Yeah.
Can you hear? Okay, sorry. Okay, this is quite a difficult question in one sense, because I don't think anybody really knows much about COVID. We're all learning about it at the moment. We have had many deaths in the UK, as you will know. We have tried to follow other countries and so on. I have a number of papers on my desk here about COVID being measured in wastewater treatment works. And certainly at the moment, I know in the UK, a large number of the water companies are monitoring for COVID-ID in the, COVID-19 in the treated wastewater going back into the river system. So I don't think we know what's in our coastal seas yet. There are many other challenges coming forward, though. There's PFOAs and PFASs coming from Teflon, and large number of there's a lot coming through the water system, the river basins at the moment, of growing international concern in terms of health risk.
Okay, then, yeah.
But I think there will be a lot of papers published on this topic in the near future.
Okay. This. So currently you are answering question from Amir Afiq. So we have another question here. Thank you very much for that question. Okay. The next question is, how sustainable the proposal of impounding the water downstream? Okay. Now we talk about the coastal reservoir. So this is the new idea of impounding the water downstream after many years of dealing with the impounding the water upstream when building the water upstream. So as we are facing the climate change, we have to come out with the new idea of impounding the water downstream and building, build up the new residential area within the catchment so that we can use the impounding water from the coastal reservoir to supply the water at the nearby residential area. So
Okay.
the question here is, how sustainable the proposal of impounding the water downstream? As for the case, we fail to control the pollution sources within the upstream catchment.
Well, the problem is, at the moment, what we've done historically is that we have built dams at the top of the catchment to hold the water for water supply. The population is often some considerable distance away from the dam, as was the case in Cardiff, for example. The water is held in dams about 50 kilometers upstream, which is quite a distance in the UK. So the water has to be transported, which is an energy requirement, from the dams to the coastal city. These cities are becoming larger and larger, particularly in China, for example. Whilst the water is traveling, whilst the water is taken in the dam and then transported from the dam to the city, we have lower flows in the river. So in many cases, in drought conditions, we have serious negative environmental impacts. So if we go back to nature as much as we can and build a reservoir at the end of the system, we are collecting the water at the end of the system. So if there's pollution in the upper catchment, at least as that water travels through the river basin, a lot of it will decay by the time it gets to the coastal reservoir. So in that sense, there is an opportunity to have better quality water through natural processes by the time it gets to the coastal environment. The other advantage, if you look at Shanghai, for example, is that the big reservoir, I've forgotten the name of it in Chinese, but the big reservoir that supplies typically 50% of the water now to Shanghai is in the mouth of the estuary. It doesn't have very far to transport that water from that reservoir to the city itself. Therefore, the carbon footprint is dramatically reduced. So it does seem that coastal reservoirs are becoming a serious option for water supply to mega cities near the coast. They should certainly be looked at alongside other alternatives, because they can offer many opportunities, including flood mitigation in some cases.
Okay then. Thank you for your answer about that. Okay. Do you have any? Yeah, we have another question here from Professor Fadil from UTM. So basically, the question is: can we model the severity and level of risk assessment in the IWRM, Integrated Water Resources Management? Because in Malaysia, we are currently dealing with the Integrated Water Resources Management. So we need to yes. In many cases, E. coli could be the major indicator for planning and mitigation strategies. So the question is E. coli.
Yes, I think we can. I think it's important, though, that the modeling that's done is truly integrated and not linked. Very often, when the modeling's just linked, we don't get the right fluxes from the 2D to the from the 1D to the 2D, from the catchment to the 1D, and so forth. So I think it's very important that the linking is done properly.
Yeah. I found that many publications nowadays that researchers had been dealing with the severity, modeling severity from the E. coli modeling.
Yes.
Yeah.
I think that can be done.
Yep. I think that's answering the question from Professor Fadil from UTM.
Oh, I didn't see that bit there.
Okay, we had another question from Dr. Reza from UTM as well. Okay, the diffusion coefficient. This is about the diffusion coefficient.
Yeah.
Between 1D and 2D model. The difference is very large. I think that's from your previous publication. From the presentation today. Would it be different when applying in 3D model? Is it something that can be measured and confirm this? Okay, yeah. I have addressed this issue as well before.
Well,
so could you comment on that?
Well, strictly speaking, if you went to a full three-dimensional model and it was and you were able to solve your problem analytically, then dispersion would not exist. So the dispersion occurs as a result of the averaging that you introduce through modeling, whether it's 1D where you average over the section of flow, or 2D where you average over the depth of flow, and 3D where you average over the layer. So you may have a layer 1 meter thick, for example, near the surface. You may have quite a strong wind. You may have a current at the surface, which is very different from that at the bottom of the layer. And this will affect, and this is, we try to represent this through our dispersion coefficients. So it is, there will be significant differences, and we need to collect more data in applying three-dimensional models. We are increasingly using 3D models, and we need to collect more data and get better representation of our dispersion coefficients in the hydrodynamic environments.
Yeah. Thank you very much for the answer, Roger. Yeah, I just want to add, because nowadays in modeling, either 2D or 3D, we have several schemes that we can come up, such as K epsilons, turbulence model, whatsoever.
That's the turbulence rather than the dispersion or the spatial averaging. So if you just have a logarithmic velocity distribution, for example, and you have a one-dimensional flume, and you put some effluent near the surface, it might travel at 1 meter per second. If you put the effluent, if it's relatively dense and it's near the bed, it may only travel at 10 centimeters per second. And yet it's still traveling in a logarithmic profile, irrespective of a K epsilon turbulence model, for example. So we need to allow for this averaging, or the difference between the surface transport of a buoyant effluent vis-a-vis an effluent near the bed, which travels very much slower.
Okay then, yeah. I think that's answering the question from Dr. Reza. Okay, we have another question here from Nur. The question is, do you think having a river basin authority is a good start to kickstart IWRM, Integrated Water Resources Management effort? Can you give an example of a successful model at the moment?
Yes, I think that the river basin authorities need to include, though, the estuary and the near coast, because whatever goes down the river ends up in the coastal waters, and cities are increasingly. I'm talking about globally rather than specifically Malaysia, but more and more countries now are finding that there's a big shift of the rural population to the urban cities. We in the UK, for example, are finding that the population is increasing as the country as a whole, but in particular, the population of cities is increasing. Cardiff, for example, has increased significantly in the 25 years that I was there. It went from about 250,000 to about, I'm not sure what it is now, but it's about 350,000. So the population of Cardiff has increased by a third over pretty well the 25 years that I was there. Yet the middle of Wales is probably far less different over that 25-year period. So it is important, in my experience, that a river basin authorities do include the estuary and the coastal basin. And the modelling also goes from the upper reaches of the basin, right, the catchments, right down to the coast.
Yeah, that's a very good idea to have a river basin authority for managing the catchments instead of having a separate authority on that. So there will be another issue of dealing with, of managing the catchment, of managing the basin. Yeah. Thank you very much for all of your questions. Yeah, I think we have several questions. I think we can go with another one question. One question is how to control the increasing in the river salinity due to flowing upstream from the ocean to rivers.
That's a good question. But certainly, if you were to build a coastal reservoir in the form of a barrage, and if you had a reasonable tidal range, as we discussed when you were in Cardiff with the Sem barrage, for example, then you could control that problem. So building a barrage across an estuary in some form or another allows you to control that issue. However, if we experience sea level rise of the order of 1.3, 1.5 meters by the end of this century, then there will be significant salinity intrusions in the rivers, changing the wetland structure, the mangrove in Malaysia, for example, and so on. So we are expecting significant changes with sea level rise over the rest of this century, which will affect salinity intrusion. The salinity will move further upstream.
Yeah, that's the issue.
Also, in many parts of the world, of course, they're building desalination plants in the estuarine environment, which also, over the long term, adds to salinity concentrations.
Yeah, that's the issue, Roger. When we are talking about the climate change and sea level rise, we are currently have a extraction plant for the water resource at one point, but then when the sea level rise, we talk about saltwater intrusion will move upstream, and how we have to think about dealing with this saltwater intrusion to extract the water resource at current point of extraction.
There was one question there which I'd like to pick up, if I may, on the screen. You didn't ask it to me, and that was the question about water wars and concerns about water wars. And I mentioned Ethiopia, Egypt, Sudan.
Okay.
That one.
Yeah, this one.
Yeah. Okay. Can I pick up this question in a general context? One of the problems we face globally at the moment is that people. Let's take cotton. So we buy cotton in the UK, for example. We don't produce our own cotton. So we get the cotton from a country, let's say Ethiopia, and they put contaminated water back into the river. So I'm buying my shirt, for example, which may be produced in somewhere like Ethiopia, let's say. I'm not sure whether we get cotton from Ethiopia, but let's assume we did. They then add fertilizers and so forth to grow the cotton crops. So the water going back into the river may have high levels of fertilizers in it. So further downstream, when you get to Egypt, for example, that water's not very good then to grow cotton in Egypt. And I think we have to put pressure on the global community to think twice and to be much more conscious of what happens with the water that's produced in a country like Ethiopia, of a product that's been bought before it travels some considerable distance downstream. And I would personally like to place far less emphasis on expecting the woman reading the news to have a different dress on every day, which is adversely affecting water quality in many countries around the world. And also, I would like us to be paying more for our cotton materials in the richer Western world, so that the farmers can be compelled to treat the water before it goes back into the river, so that the water in Ethiopia, by the time it gets down to Egypt, for example, can be clean again, so that the people in Egypt can use clean water. Sorry to refer to Ethiopia, Sudan, and Egypt, but this applies many, many countries all around the world. So the more we can teach people and educate people about virtual water and the impact they may have on water quality in another country is really important in my view. I know in India, many, many farmers commit suicide because of water problems, and that's terrible.
Yeah.
Excuse me.
Okay, I think that's all. Thank you very much, Roger, for answering all of the questions.
My pleasure.
That's all. That's all. The questions from the audience. We have several other questions, but because the time is 5 now, so I think now is the end of our lecture. So thank you very much again, Roger, for spending time giving lecture when based on the distinguished lecture series that have been organized by UTM Engineering. So I think I should pass over to Professor Rafiq. Over to you, Prof.
Amirul, thank you so very much. And to Roger, our deepest gratitude to you for sharing your knowledge with all of us. Thank you for accepting our invitation, and thank you for sharing your work on water security. It is an important topic for us here in Malaysia, and UTM has a dedicated Center of Excellence on water sustainability. And to all of you watching this program, thank you as well. I was told that we have viewers from the Europe, the Middle East. We even have viewers from New Delhi, Roger. They must hear the point that you mentioned, that whatever that we do here in our countries affect those people in India. And wherever you are in the globe, don't forget to like our Facebook page because we have many more interesting lectures for you. Do share this video to all your friends and colleagues worldwide. Thank you for watching. I'll see all of you in our next episode of UTM Engineering Distinguished Lecture Series. Bye for now.
Thank you very much.